Hello everyone and welcome to a discussion of the design of NASA Space Launch System, or SLS, ahead of the Artemis 1 mission in which it is going to launch the Orion spacecraft to the moon. SLS is designed to make use of components from the Space Shuttle program as much as possible. It is making use of the Space Shuttle's main engines. In the case of Artemis 1, literally reusing them from the Space Shuttle program. They are not new engines for Artemis 1. It is using some of the cases for the segments of the SRBs, the solid rocket boosters. The solid rocket boosters for SLS are 5-segment instead of 4-segment for the Space Shuttle program, but the segments from the Space Shuttle program were fished out and basically refilled, repacked with solid propellant, and some of the cases on the SRBs are ones that were from the Space Shuttle program. So there is that, and yeah, that's all well and good, so why did it cost so much? Basically is the question, right? It's making use of all these things that were from the shuttle program. It should have been cheap. That was the theory, and frankly, there is no good excuse for the price of SLS at this point. I'll be frank about it. I think they need to investigate, basically. But if we're going to narrow it down to one root cause, it is the main thing that they could not simply take from the shuttle program, and that is the core tanks. There is no way that these could be designed the same way as the shuttle tanks. They are completely redesigned, and let me explain why. Let's take a look at the space shuttle. Now, when we see the space shuttle, first of all, it is rather small compared to SLS, and the main tank of SLS, of course, has to be extended because the space shuttle only had 3 of the SSMEs, the space shuttle main engines, whereas SLS uses 4. So it has to be lengthened at the very least. But actually, it has to be completely redesigned because the engines for the space shuttle are not pointing through the hydrogen tank of the space shuttle stack. Instead, they are actually pointing at this intertank section, which is highly reinforced. You can sort of see that, and through this strut. So basically, the inner tank is bearing the brunt of all the force from the space shuttle main engines. It is also bearing the brunt of the thrust from the boosters. They are attached up here, and basically they direct their thrust up through there and not at the hydrogen tank, even though they're braced down here. Both the shuttle and the boosters are braced down here, but those are just braces. They are not actually bearing the thrust. And so the hydrogen tank is relieved from all of that pressure, all that thrust, all that force, and it's just basically sort of hanging off of the inner tank. That means that it can be much lighter. In SLS, it can't do that. They can't make it like that because the engines are directly underneath the hydrogen tank. So the whole thing, the largest structural element of the rocket, needs to be reinforced in that case. And because of that, we get a very big difference between the mass of the shuttle's external tank and the mass of SLS's main tank. If we take off the boosters here and reroute to the tank and take off the shuttle, what we find is that fully fueled, the external tank is 764.8 tons. And most of that mass is the oxygen tank up here. So if we take out the oxygen, we'll see it only goes down to 133 tons. That means the huge hydrogen tank only has to deal with 133 tons worth of weight. But the shuttle main engines produce 700 tons of thrust. You take the thrust rating in kilonewtons, divide by 9.81, and you'll get the tons of thrust, which is basically what the engines can cause to hover. That is what they can lift. So about 700 tons of thrust at maximum is what they can produce, but this huge tank now does not have to deal with that because the shuttle is pointing through the intertank, and so it just needs to deal with the 130-ish tons of hydrogen. Actually, about 100 tons. This is including the full dry mass. The oxygen tank would have a payload on top in the case of SLS, but the oxygen tank is already pretty strong since it had to deal with the whole load of the oxygen, which is much heavier than the hydrogen. And so it's about 600 tons that it had to deal with. So an extra 150 tons on top of it's no big deal. But the hydrogen tank, which is huge, but doesn't have much in it because hydrogen is very not dense. It didn't have to be so heavy, and so when we take a look at the mass of the total system here, the whole tank is only 27 tons in the super lightweight configuration, which is what the space shuttle system ultimately ended up with. So that's 27 tons. When we go back to SLS, we'll take a look at it. So I will also remove the engines and the thrust elements so that we just get the tank. So here the full tank is 1,050 tons, which should make sense if the 3 engines were about 750 tons, let's say. So that's 250 tons per engine. Then we get about 250 tons per engine here too, but a little bit more than that, right? And when we empty the tanks, first of all, the oxygen tank we again see is the bulk of it. The hydrogen tank, now we are only at 210 tons. And when we remove the hydrogen, we get about a 70-ton tank here. It's probably a little bit heavier than that, to be honest. And yeah, that's heavier than it ought to be. If we just took the ratio of the engines, you know, add an extra third to it, we would not get this much. We would get about half of that. So that is the effect of having the engines directly underneath. And we can see that it's not because SLS is being strengthened for future boosters or anything like that. We know that because we can compare to the Energia rocket, which the Soviet Union made to launch Buran. But in the case of Buran, the engines, the main engines, were not on Buran, their space shuttle. The engines were on the bottom, just like they are with SLS. And in the case of the main tank for the Energia rocket, it is basically exactly the same as SLS. It's a little bit heavier because we've improved over time, of course. That was 30 years ago. But yeah, it's on this order or heavier. So again, we see that moving the engines to the bottom has this effect. So this is a feature of the space shuttle system that people don't appreciate, that because the engines were on the space shuttle, not only could they bring those engines back, but it made the whole stack more efficient by relieving the hydrogen tank of stress, and therefore the hydrogen tank could be made lighter. But that means you can't just port the design of the hydrogen tank into SLS. And the hydrogen tank is the largest thing here. So you have to completely redesign that, and if you completely redesign that, that turns out to cost a lot more money than they initially thought. So that is, I mean, not as an excuse, I still think it was all more expensive than it ought to have been. But anyway, that is one thing to consider. That is one thing that they could not simply take from the space shuttle and reuse. They used the same diameter tank. That might have helped somewhat, but ultimately the whole thing had to be redone because of the way the engines were placed. So that's one design consideration for SLS. Let's take a look at the upper stages. What we have here is not SLS's final form. This is SLS Block 1, and this is not how SLS was basically designed to be. This is an interim situation with an interim cryogenic upper stage. There's the ICPS, which stands for Interim Cryogenic Propulsion System. If we take off the launch escape system and the aero cap, and let's also just take off the panels here so we can see the service module, which I'll talk about. And we can take off the rocket that we've already discussed. I'm not going to discuss the SRBs in detail. They're probably more expensive than they ought to be too. But anyway, there they are. But we are going to discuss this stage. This is a borrowed stage from the Delta IV system. It is not the stage SLS is meant to carry, which means that the core is overpowered for carrying the stage. But it turns out that this was sufficient to send Orion over to the moon. SLS was not designed with the intention of just sending Orion to the moon. It was meant to also send landers. This was, of course, all designed before Lunar Starship, and of course other landers may still be developed as an alternative. Lunar Starship is very large and might not always be taken advantage of fully, so who knows what's going to happen down the road. And I have some proposals. I am, after all, a designer at heart, so I have an idea for how to use SLS. We'll get to that later, not in this video. But this is sufficient to get Orion over there for Artemis 1, but it's not making use of the full rocket because the stage that they wanted to have is just not ready yet, and that is this stage, the exploration upper stage. It has 4 engines of basically the same type as the ICPS has 1, except they're the RL-10Cs. That one is the RL-10B2, and for our purposes it's not a huge difference. But this is a much more capable stage. The rocket as a whole cannot send as much to the moon as Saturn V did. It's rated for about 37 to 38 tons to the moon, whereas Saturn V could launch 45 tons to the moon. But the mission profile is quite different, and that leads to some interesting possibilities as far as what it can do. The Orion service module has not been my favorite thing in the world, but based on my test in the previous video where I tried it out with Principia and everything, it seemed like it had enough repellent that it could tug some module into a high orbit around the moon. Something like a Lunar Gateway module, or a supply module for Lunar Gateway, or a component of a lander. Dock it to Lunar Gateway, and then if the lander comes in multiple pieces, they can be assembled together. So it could potentially do that. And it had enough fuel for that, and the reason it had enough fuel for that is because it is getting into this high orbit, which only takes about 300 meters per second. And given that it might not need the service module that Apollo had. Apollo had a much larger service module, but that was meant to get landers all the way down to low lunar orbit, which costs 800 meters per second. So that's a lot more. And then, of course, the spacecraft would then have to also leave getting out of low lunar orbit, taking another 800 on its own, but that's without the lander. Altogether, the budget was about 2,800 meters per second if you consider the command and service module. So while it's tugging the lunar lander, of course, that gets cut down. So in this case, it's about 1,500 meters per second as far as I can tell, and so that's a lot less. But then if you're getting into the high orbit, the requirements are a lot less. So in future videos, I'll explore what we can do with that now that I have some ideas. But given that high orbit, there are some trade-offs. Just like there were trade-offs when it comes to where you place the engines, whether they're at the bottom of the stack or whether they're on the shuttle, there are some trade-offs as far as getting into a high orbit around the moon versus getting into low orbit. Getting into the high orbit makes it easier to capture and leave for the service module, but it makes it harder for the lander. The lander now needs to go all the way from the high orbit down to the surface and then back to the high orbit. But there are multiple ways of doing this. None of the ways of doing this that I would think of were actually proposed during the lander competition. So let me just broach this generally speaking. I hate all rockets equally. You've heard people say love all rockets. I hate all rockets. I'm a science fiction person. I want the Star Trek Enterprise or X-Wings or Millennium Falcon. But I'll deal with what you give me. I'm not going to get in the middle of SLS versus Starship fights. I'll deal with what you give me. I've played around with SLS. I've played around with starships. I've designed my Shinkansen spaceplane to be refueled by both. The Orion 3 spaceplane can be fueled by both. It is specifically sized so that either system can refuel it. And so that's the way I think. I'll take what you give me. But, so if EUS is what I'm given, I can figure out a way to use it. The things that they proposed didn't use it properly as far as I'm concerned. So I will explore that in future videos. There is a way to use it that will help. that isn't a complete waste of time. And the SLS is designed to use this stage. I don't think it is a bad stage in terms of efficiency. It is. These are very efficient engines. They're very lightweight engines. Some people, looking back to Constellation, think, well, if only we had the J2X. But the J2X was a heavier engine. It's a less efficient engine. It has more thrust, but that's really not necessary once you're in space, which is where this stage would be. So if you want to improve on anything, maybe you could improve on the thrust down here. The RS-68s weren't the best for that, but if you could improve the thrust down here, then you could have a heavier stage, though then you would be getting to the burn time limits for these engines. Right now they're basically at the limit for what they're tested for as far as burn time, but maybe they could be tested for something longer. So there are possibilities there, but simply carrying a high thrust engine is pointless when you're already in space. So you want the most efficient engines possible, and these are basically it, unless you're going to get a nuclear system. I used to have qualms about the EUS. I used to think about having a high thrust engine, but basically having actually tried things out, I realized that it's not the best thing to have a high thrust engine in that place. So a lot benefits from just actually trying it out and seeing what works, and then you realize, okay, there is some logic to it and you can work with it. So I can work with this. I can work with many things, and we will see how I work with it in the future. But anyway, so the basic points here are that it couldn't really be designed fully based on the space shuttle system, and that was one cost. This is a completely new stage, and it has to be tested separately, which is another cost. The RL-10s are super efficient and also not cheap, so that is another issue. Still, I think there's no reason that everything should have costed the way it did, and I think that is a shame. But we have what we have. So I will see what we can do with this, and when Starship's time comes, I will see what we can do with that. And that is all I have to say for now. So I hope everybody gets to enjoy the Artemis 1 mission, and we will see how well it does. With that, thank you for watching. I hope you enjoyed this video. If you did, please do press like. If you have any comments or suggestions, please leave them in the comment section below, and I'll see you next time.